So I know we already did this one, but if you put the word homework up here, that is actually one of the things I'm going to ask you to do. Homework. Basically, their assignment slide is going to say, I want you to go ahead and sketch what the phases of the moon looks like. And say what they are. So we are, let's see, the moon we just looked at looked kind of, to me, somewhere in between these two. Does that seem right? Okay. And actually over here, this is what we call waning. We talked the other day. What is today? Friday? We talked Wednesday. This is waning. You should all have that in your notes. And this is waxing. And it works pretty good if you hold up your right hand and whatever on the right is going to continue. So these are waxing, getting more and more and more. This is a full moon. Okay, and these are waning. So what lunar phase is missing? New moon, exactly. You got it. New moon. Yep. Okay. So this is kind of a subtle thing. Does this look like a crescent moon? Does it kind of look like a crescent? And we've been talking about you hold out your hand, what's over on the right is going to continue. So this would be like a dark, it's going to continue getting dark. That's my point. So this is a waning crescent. But sometimes you can actually, when the moon is a crescent, look up and you see the normal part, but you also see kind of the rest of the circle. Okay, so this would be the normal part. Here's our crescent. Make sure I'm going for crescent rolls. And this right here, okay, is what we call earthshine. Like, how could the moon be earthshine? Okay, well, here's the deal. Basically, we're only seeing that part dimly lit because the light from the sun is shining on the earth, and part of that light is going up to the moon to light it up. So kind of emphasizing earthshine like this. Okay, it's definitely a crescent, okay, but the earthshine part looks like this. This is daytime for the earth, and it's lighting up the moon right here, and we are over here, and so that's why it is like that. Okay. So one more topic about the moon. When I picked out things that I'm hoping you guys take the rest of your lives. The phases of the moon is one of them. Seeing the moon in the daytime is another one. Another thing is tides. So living here in Midwest, we're not near an ocean. Okay, but some of you might have experiences visiting the ocean. Okay, and you know that actually there's a high tide where basically the water comes on the shore, and then there's a low tide. And that's all caused from the moon, the location of the moon. So the thing about oceans is they are affected by gravity. So this kind of blue right here is kind of showing you how maybe oceans would be basically lifted towards the moon. Okay. So, yeah. So basically you end up with, and it's independent of the phase of the moon, but where the moon is. Where the moon is, as the Earth spins, actually has a high tide. So the thing about it, though, is where the moon is has a high tide, and the opposite place where the moon is has a high tide. So actually you see two bulges. This is where the moon is, has a high tide, and the opposite place also has a high tide. So that's why you get it every 12 hours as the Earth spins. So I have some photographs to kind of show you the difference between, this is high tide, I'll put it H for high, and this is low tide. H for high tide, L for low tide. So if you're looking for shells, you want to go low tide, right? Instead of high tide. And I have another example for you here. Okay, high tide on the bottom, and low tide on the top. So, all right. So there's a little subtle difference between high tide and high tides. Sometimes the high tides are especially high, and we call that actually spring tide. And that occurs when not only the moon gives a tug to the Earth's oceans, but also the sun gives a tug. So the times when the moon and the sun are on the same side of the earth would be new moon and full moon. New moon and full moon. They can actually work together to create especially high tides. Hurricane or tropical storm, I can't remember, the one that hit the New England states. And Chris Christie was, I don't know. But I wish I could think of it. I'll think of it. But anyway, it was a hurricane that went north, and it was weird to hit. It's weird to have something do this. It's like the New England states up here. Okay? And the thing about it is the hurricane hit when it was a springtime, which kind of worked to the disadvantage of people getting slammed by what we call storm surge. Okay, so, all right. The opposite of spring tide is neap tide, so you'll have a high tide every 12 hours, but in this case, the sun kind of works against you. So instead of being on the same side of the moon, basically you have the sun at right angles to the moon. So our options there are at first quarter or at second quarter. Okay, so in that case, the sun works against high tide. So they'll have high tide, it'll just be diminished high tide. All right, then the last thing is eclipses. I like that we were able to kind of look or think through maybe a little bit about eclipses. There's two types of eclipses. There's lunar eclipses and solar eclipses. So a lunar eclipse happens as basically the moon kind of scoots into what we call the Earth's shadow. So the first example of a lunar eclipse here is this, where if this is the sun and here's the Earth, and if this is the moon, we would say the moon is in its full phase, full moon. Does that make sense? Well, if it goes just right, kind of not too high, not too low, basically it's going to run into what we call the Earth's shadow. There's two types of the Earth's shadow that it casts. The Earth's shadow casts a really dark shadow called the umbra. That's especially dark. And then it has kind of, it looks like a bullseye, kind of an outer shadow called the penumbra. And that's a lighter shadow. Okay, so if the moon goes through the Earth's umbra, that's when you get a cool total eclipse. And we were talking about the blood red moons. So at what we call totality, when it's entirely into the Earth shadow, it looks like this. Then the other type of eclipse is a solar eclipse. And in order to be a solar eclipse, the moon, which is right here, moon needs to basically cover up the disk of the sun from our perspective. And again, it has to be lined up just right. And then it will cast a shadow right here on the Earth. And those folks will get to see it. Can't remember, I don't think I have, like the dates. If you, I don't know the exact date, but August 2017 is when we have a total solar eclipse going to happen in our neck of the woods. We'll hope for clear skies. So this is just showing you a solar eclipse. This, of course, in front of the sun would be the moon, and you kind of see actually that's the corona of the sun kind of squirting out behind it. And this is the shadow that is cast on the Earth. So this last slide just is showing you how come the moon kind of misses the whole eclipse. And it's showing you the Earth in 4 locations, okay? And of course we know what orbits the Earth is the moon. And just like the Earth has what we call a plane of the ecliptic, okay? So also the moon kind of has its own little plane that it orbits the Earth in. And that's kind of being shown here with these kind of slanty things. And it's tilted, like the slide says, 5 degrees outside of the plane of the ecliptic. So it's a little bit of a hit and miss. Okay, so here is your assignment. Now notice I'm kind of doing something different. I have the first 2 things are not in your textbook. Okay, so the first 2 things are not in your textbook. The first thing It says sketch and label the phases of the moon in order as they occur. Basically, the slide I showed you when we started out. And then it says describe the two main features visible when we look at the moon. Remember we talked about the man in the moon? You know, we have these, I'll give you a hint for that one. I'm wanting you to tell me about the light regions, the regions that appear light, and the dark regions. And then normal questions, short answer questions on page 508 and 509. Questions number 8, 9, and 14. Sure everybody got this. Okay, ready? Ready. So let's take a look at constellations. Okay, so constellations, remember I told you I like that stellarium.org to get a sky map. That's what I would do if I was you. Stellarium.org. So you need a computer, but it's a program that you can load onto your computer and you can have sky map. It's pretty good. Okay, so stars, of course, we're talking about kind of sets of stars. And I wish we had more time and it was nice and dark and we could go out and look at constellations. The problem with looking at constellations here actually is if you have stray light and it's hard to see, the stars don't pop out. So it's kind of, that's a thing you fight against. But in order for you to actually be able to see the Big Dipper, for instance, as a set of stars, okay, you got the bowl and the handle, we have a slide coming up with the Big Dipper picture of the Big Dipper and the stars that make up that what we call an asterism. We need to talk again about parallax. All right, so parallax, and this is an experiment. Not only did I want you to go outside today, but I want you guys to do this little experiment. So basically, you hold your finger in front of your nose, okay, and then you have to close one eye, okay, and then close the other eye. And everybody do it. Hold your finger in front of your nose, and wink one eye and wink the other eye. It moves, yes. Actually, that's called parallax. Now take your finger, it's in front of your nose, and now move it farther away and close one eye and close the other eye. Does it move more or less? Less. I put it even farther, even less still. So actually, if something's close to you, what you're doing is changing your position. So right now I'm over here looking, and right now I can't leave very good. I'm over here looking. Okay, right now I'm looking over here looking, over here looking. And actually it looks like if something's kind of close, it looks like it's in different positions against the back. That's parallax. Okay? So the deal is, and this is another thing about parallax. So for instance, these people, the guy and the girl, are both looking at the same tree. Notice that he sees it against the mountains. He sees it over here, okay? This is this guy. And she sees the top of the tree over here. Okay, can you see where that's different? Again, the tree is kind of close, and basically they're at two different positions looking at the tree, the background. Well, the thing is, and what this has to do with astronomy, and this actually goes back to, you guys had a homework where you told me the difference between the geocentric model of where we live putting the Earth in the center and everything orbits the Earth, versus the heliocentric, which we know to be the truth, right? The sun is in the center and the planets orbit the sun. Now, if the Earth is moving, if the Earth is orbiting the sun, okay, 6 months apart, you know, I could put the Earth, excuse me, put the sun right back here again. 6 months apart, we are definitely different locations. We're kind of like the guy and the girl, 6 months apart. So we'd be here in January, and we would be here in June, okay? So the deal is, if something was kind of close, it would like scramble. It would look different against the background stars. And that was one of the things that people fought. They're like, hey, if the sun is in the center and the Earth moves, then those beautiful sets of stars that we see, I mean, they should be kind of scrambling as we are relocating in space. Okay? So, in fact, we can use parallax for instance, here's this nearby star. Okay, if a star is kind of like your finger, relatively nearby, okay, and we relocate, we can actually see it change. It wouldn't be a good one to be part of a constellation because actually it would move a little bit against the background stars. But the other thing is, like, if you take your finger and if you could like basically dislocate it from your shoulder, I know it's kind of gross, and basically make it clear back there against the wall, and then if you wink your eyes back and forth, you'd be like, it doesn't change at all, because basically it's so far away. And so most of the stars, we see no parallax. But a few of the nearby stars, we do see parallax. Okay? So that's that. What's that?
I don't even recognize when you're flipping the pen.
I'm tricky?
Mm-hmm. Okay.
Oh.
It's like I just listened to you and I'm like, oh.
Oh, she flipped it onto something new. Yeah. Okay. So constellations, actually there are 88 constellations, and I brought something called a celestial sphere. But what they did was take all of the stars ever, okay, and they like basically made boundaries. So this constellation are all of these stars, this constellation are all of these stars. There's boundaries. So like for instance, if you look at Taurus, you're like constellation Taurus, which is the bull, you're like, okay, I recognize the bull, but everything in that boundary is those stars. So 88 constellations, but they're unequal. And you probably can't see, well, you can see it a little bit. So actually, these are the 88 constellations, alphabetically. And some of these you'd be like, I don't recognize that. That's because, as you might imagine, there's a whole set of constellations we never see unless we go to the southern hemisphere. Okay, so we're kind of limited to the constellations we see. So a lot of the constellations actually came from Greek and Roman mythology. So this is also constellations, but has like the pretty picture. One of the things when I talk about constellations in my other class, or I guess when I talk about constellations with anybody, they're like, I don't see that. So we talked about the Big Dipper. Do you see, here's the Big Dipper. Okay, so the Big Dipper actually is a subset of the Great Bear. We call Ursa Major. Major. Cool. Did we talk? I don't think we did talk yet. But while I have this slide up, everybody wants to know where Polaris is. Actually, if you found the Big Dipper, like here, you can find Polaris if you take the two bowl stars and go kind of in a straight line. Actually, I think we did talk about this the other day. The two bowl stars go in a straight line, and the next kind of bright star is Polaris. And that is Polaris on this sky map. I have a better map coming up. So, 88 constellations. The sky is broken up in 88 constellations. Now, in science, sometimes we use models that are not the real deal, but the models kind of help get us down the road. And so, to me, the concept of a celestial sphere does that. So this, it's been around for a while, so the plastic was brittle and it broke down. But Oh my goodness. There's the Earth inside of there. But this is called the celestial sphere. And these yellow dots are stars. Okay, so again, 88 constellations. Okay. And inside the celestial sphere is the Earth. And does it seem like we're kind of going backwards? Like, really? We talked about this, and the Earth orbits the sun. Things don't orbit the Earth. Okay, but the model of a celestial sphere works pretty good. Okay, so if I go ahead and spin this, I spin the Earth, okay, actually what that's going to do is if you're on any location, as I spin the Earth, you're actually going to see different stars. And we do see different stars. I don't know if I think I mentioned this the other day. That will be Polaris. Actually, it's not a bad fit for Polaris. And if you're able to sit outside and watch the stars move in one night, what you'll see actually is stars will go counterclockwise around Polaris. So I just dare you to do it. It goes counterclockwise around Polaris. Yeah. So celestial sphere. I know it's kind of strange. So here's a figure from your textbook that is basically this. In the center is the Earth. Okay, notice we have the Earth's axis of rotation is that dotted line on the figure. Axis of rotation, it spins. So we have some important, and actually there's a homework question I assigned for you guys to also turn in for Monday. If this is the Earth's axis of rotation, let me pick red. If this is the Earth's axis of rotation, it actually ends up showing on the celestial sphere the south celestial pole, and on the celestial sphere the north celestial pole. So as I'm holding this carefully, okay, this would be the north celestial pole, and this would be the south celestial pole. There's one more feature of the celestial sphere, and that is the celestial equator. And can you actually see this seam right here? It lines up with the Earth's equator inside. That would be the celestial equator. Also drawn on here, I think I have it on this, is the yellow line actually is the path that the sun appears to make against the background stars. Now, the sun does not orbit the Earth, right? The sun does not orbit the Earth. Say it with me. No, I know. But on the celestial sphere, the sun actually will make that path against the background stars. And we call that that actually lines up with the ecliptic. That ecliptic, or the yellow line, the path of the sun, actually, if you were to do an angle, if you're into kind of math, if you were to measure this angle right here, this is 23.5 degrees. I think we talked about the Earth's tilted axis of rotation, and instead of being straight up and down, it's tilted 23.5 degrees, and actually that's what creates this too. All right. So one last thing I have about the celestial sphere is sometimes, like if you're out at the observatory, they'll say, well, where do I need to go to see that object? And actually, we can take the celestial sphere and break it up into coordinates. So they're like, oh, I need to go here and here. Okay, it's like coordinates on the celestial sphere. We call that actually right ascension and declination. All right, now just some pretty pictures. The dots are the stars. And we've been talking earlier and then today about the Big Dipper. See the Big Dipper? They're pretty bright stars. But really the Big Dipper is kind of embedded in the Big Bear. We can use this is what we call the bowl right here. Hopefully it looks like a bowl, and this is actually what we call the handle of the Big Dipper. So we can use the far bowl stars here, and sometimes they're called pointer stars, and what they point to is actually the North Star. The North Star right now for us is Polaris. And the North Star is in the handle of the Little Dipper. Now, I'll circle the Little Dipper, but I'm warning you that if you're outside, sometimes the Little Dipper is hard to make out. To me, these are especially hard to see. unless your skies are really dark. So there's the Little Dipper, and it's in the Little Bear. Go figure. Another important star that kind of looks like a UFO sometimes is if you take the handle of the Big Dipper and you arc it over. The key term here is arc. You arc it over. You can actually arc to a star called Arcturus. The name of the star is Arcturus. It's in the constellation Bootes. Then Leo and Virgo are underneath in this picture anyway. Okay, so yeah. Polaris is an important star because everything spins around it right now. And the reason things spin around it is because our axis of rotation is pointed to it. So everything kind of spins around it. But it's not the brightest star in the sky by any means. That's another misconception. Sometimes like, ooh, Polaris, it should be really bright. No, it's not. It's really important, but it's not really bright. Okay, so throughout the evening, stars appear to rotate counterclockwise. All right. So in other words, star trails would go like this. Okay. Another set of stars, and I think we talked about this, that if we go ahead and make that the sun, okay, and I'm going to be the Earth, of course we know that the Earth is going to orbit the sun in a year, and I definitely will have different stars to see if I'm over here, okay, versus if I'm over here, I'll see these stars. If I'm over here, I'll see these stars. Because, of course, I only see the stars when I'm nighttime. Okay? So these are actually some stars we're going to see in the winter. I love Orion. Orion is a beautiful constellation. All right, the last one, stars you generally see in the summertime. On the next week, before your test, we will talk a little bit about our galaxy. And these red dots here actually are from our galaxy. They're from what we call the plane of our galaxy. So if you've ever heard somebody talk about the Milky Way, it looks like spilt milk across the sky. Okay, what they're actually looking into is kind of the disk of our galaxy. All right, and then for this one, all I came up with was a normal assignment question, page 543, question number 2. So that's just a little bit about constellation. A little bit of this, a little bit of that. And so next Thursday is, and that's all I'm going to do today. So next Thursday is your unit exam. So I'll try to kind of see what that unit exam is going to look like so I can give you a review sheet next week. But Monday we're going to still talk about astronomy, new stuff in astronomy, and probably Wednesday too. So.
Can I determine how we're feeling on Monday or Wednesday, so I won't be here Monday?
We can talk about it. But, okay. All right, ma'am.
If we don't have time to go over the review sheet in class, are you going to set up a time maybe we can go over it later before the test, or?
Maybe. Is that the question Heather asked is if I'm kind of wanting to still kind of cover new stuff even on Wednesday, would I set up another time to go over the review sheet? And yeah. Okay. There's a good chance what I'll do is just take part of Wednesday to do new material and maybe part of Wednesday to go over the review sheet. How's that sound?
Because I won't fit over the test.
Okay. Okay. Thanks for. We'll plan on something like that. Okay. So Wednesday, as a minimum, we will take part of it to go through the review sheet. Because that's the easiest to get us all together in class. Yay! All right.